Hi everyone, I'm Rohit Kumar Singh, the teaching assistant for Nuclear and Particle Physics course. Uh, the instructor of the course is Dr. P. Paulus from IIT Guwahati, NPTEL, and I'm the TA for conducting this live session on every Saturday. So this is the 7th live session so far, and so today we'll discuss some concepts of quark model. I will just try to recap some basic things about you know uh, how we uh, how we group together different uh, baryons and mesons. So I think maybe this is not clear from the lecture, so I'll try to shed some light. Okay, and then we will go through some examples, some problems. Okay, so let's start. Sorry. So yeah. So first I want to just quickly discuss something related to groups. Okay, so uh, you must have heard or learned about rotation group called SU2. If you have done some courses in mathematical physics or even in quantum mechanics, you might have came across this term, rotation group of SU2. So what are groups? So groups are basically set of some elements. Okay, and so so SU2 means spatial unitary group of uh, 2 cross 2 matrices. So SU2 means spatial unitary sorry groups of okay, so 2 is basically the dimension of the matrices. Now what does it mean? So first set of all the unitary 2 cross 2 matrices is known as group U2. Okay, so this is a basic definition of U2 group, unitary group of 2 dimension. Okay, it is just the set of all unitary 2 cross 2 matrices. Okay, do you know about unitarity, or should I explain? So basically unitary means if you have some matrix M and you have a Hermitian conjugate, you should get a and you multiply them, you get a identity matrix. So this is unitarity. Okay, and then What does it spatial means? So spatial is, so if all the matrices, if the determinant of all the matrices is equal to 1, then this group becomes SU2. Okay. Sorry. Is it clear what SU2 group is? Now, so then so there are some mathematical structure which are assigned to the group. So I'm not going into much detail of group theory, just I wanted to just tell you some terms. So there are something called generator of a group. So this generator denoted by JI is called the generator of the group. So I'll tell you what its significance is later. But for SU2 we have generators half sigma I, where sigma I are polymatrices. Now this polymatrices you must have seen while studying quantum mechanics. So these are given as this. So sigma 1 is 0 1 0 0 I minus I, and sigma 3 is okay. So basically this is the generator of this rotation group SU2. Okay, you know what, and okay, then after generator there is something called basis of a group. So basis for SU2 we have fundamental basis, which is this is the spin up and spin down. So these are the basis of this group. Okay. And then what we call SU2 algebra is just the algebra of generator JI. So you know that you must have seen that these sigma i's, they are related to each other through these commutation relations. So sigma I, sigma j commute like this, something sigma, right? For example, sigma 1 sigma 2 is equal to I sigma 3. Have you all seen this before? I mean, you can just try. You can so sigma 1 2 3 is given here. You can just try to see if you get this thing. Okay. So similarly, in general, we can say that the algebra of generator JI is like this. So commutation of J I and J K. And this epsilon JKL. So this is I forgot its name. It has a name. So what it is called? Okay, so whatever. So it is one when I mean when this JKL are in consecutive cycle. So if J is 0, K is 1, K is 1 and L is 2, then it will be 1. Otherwise, if it is in some different order, you will get 0. Okay. So this is its property. I don't know if you all know this or not. Are you familiar with this? Hello. Sorry. Yeah. Hello. I cannot hear you. I don't know. Can you try speaking again? Something is. I cannot hear you. Sorry. Wait. Let me. How to get the audio in my iPad? Something is wrong with my speaker. Okay. Can you write in chat whatever you are saying? Okay, not familiar with it. So okay, so yeah, for now just remember this. So this is this is the sorry. This is the algebra, and what does it mean is, so J1 J2 is equal to I J3, and if you have J1 and J3, then it is 0. Okay, so J1 commutes with J1 not 0, it will be minus of J2. Yeah, okay, so if you have if these things are in order like 1 2 3, you will have positive. If these things are in different order, so 1 3 2, you will get negative, like this. Okay, so for now just remember this. This is this will come in if you study group theory or some mathematical physics courses. It has a name, I forgot its name, but this is what it represents basically. Okay. Okay. Now, so this is what we call the algebra of the generator. Okay, so these are just terms, if you read any books or anything, so that you have some idea what is meant by the algebra of a group. So algebra of the group is just the algebra of the generator, which is this thing. Okay. So because because of this property of sigma matrices, this algebra, you can calculate various things. So you can operate it on this basis, and you can get the creation and annihilation of operators. So you can go from this spin up a state to a spin down a state, applying a annihilation operator, or you can go from spin down to a spin up, applying a creation operator. So which you do in the case of quantum mechanics, when you study the spin of the electron, spin of a particle. So yeah, if you have not gone through, if you have not done a course on quantum mechanics, then this might be a little confusing for you. So yeah. Then okay, so then we were studying about isospin. So like the spin of electrons or charged particles, uh, we saw that the neutron and proton are considered as are grouped together using isospins, right? So neutron has isospin, proton has isospin 1/0, and neutron, proton is assigned this 1/10 state, which is isospin, down, you can say isospin up, and then, or you can say I3 equal to minus half, and then neutron is this, this is plus half, this is minus half, right? And so the SU2 of isospin grouped together neutron and proton, right? Like isospin of isospin of ISO2 of, for example, ISO2 of spin group together the different spin of charged particles, so spin up and spin down. So like this SU2 of isospin group together neutron and proton. So this is the analogy, okay? Now since we have this isospin, so for the spin group, we have these generators called polymatrices, and you have this basis. So in isospin group, we have the basis as this proton and neutron states, and then we also have generators here which are similar to this polymatrices, but I am not going into much detail. So I just wanted to tell you how this why we have a group structure. Okay, so now what happens is you can combine so yeah, you can combine these two isospin or two spin half particles, okay, and you can get a composite representation. So this is called, combining representations of groups. So then the composite, so suppose you have two spin half particles. Now how do you combine them? So we can write the composite system of two spin half particles so symbolically you can write it like this. So what does it mean? So if you have, so suppose two particles JB spin half, and it can be grouped together with J equal to 1 and J equal to 0, right? So J here is the spin, and this is symbolically represented by this expression, okay. Similarly, you can group three spin half particles. So then three spin half particles, symbolically you can write it like this. So since 2 cross 2 we had this thing, and then this grouped with 2, so you get 3 cross 2 plus 1 cross 2, and in total you will get 4 plus 2 plus 2. So what does it mean is, so 3 spin half particles grouped together into a quartet of spin 3 half, because so quartet you will only get when you have a spin 3 half, right? So that you can get minus 3 half, minus half, half, and then 3 half. Then only you can get a quartet. So that's why to get a quartet you must have a spin 3 half, right? So spin 3 half and then 2 doublet of spin half. So spin half, for spin half you will have minus half and half. So this is a doublet, okay. So 3 spin half particles can be grouped together like this. So why I am doing this? So as to so that you can understand how we obtain the meson, baryon octet or decuplet that sir is teaching you in the lectures. So this is the origin basically, okay, because you have sir, could you explain how we got 3 cross 2 as 4? Okay, so this you understood, right? 2 cross 2 can be written as 3 plus 1. So the rule is uh, if you multiply this you get 4, so 3 plus 1 is also 4, right? And also you can do 2 plus 2, but that doesn't make sense because uh, originally you already have two spin half doublet. So similarly here 3 cross 2, I mean, so just multiplying this you get 6, right? And so uh, 6 can be break down into either 4 and 2 or 3 and 3, right? But so this you can also get 3 plus 3 plus 2. But the problem is this is this is kind of redundant, so this will give you uh, two two spin I mean, so this will be just two triplets, spin half spin 1 triplets, right? -1 0 1, and then again -1 0 1. If you consider this, so this is redundant, and why you will group something into two of the same species, or maybe this is allowed, but I'm not sure. Something should restrict this. Maybe because the states will be same, and yeah, I don't know. Something should not allow this. But so wait. Grouping in triplet doesn't give. What you're saying? Grouping in triplet doesn't give spin halves. Grouping in triplet doesn't give. No, that is not true. I mean, that is true, but so what I'm saying is, wait a minute. I removed group together into a quadruplet. It was quadruplet, right? Quartet. Sorry. Wait. I am coming to your issue. Okay. Yeah. So. So we have 3 cross 2, and you are saying how we get 4 plus 2 from there, right? So basically this is the symbolical representation, okay? And for example, grouping, I mean, let me go to first here, okay? So what we had here, so 2 cross 2 equal to 3 plus 1, okay? So why not this was 2 plus 2? This is also fine, right? But here what happens is, originally you have spin half particles, I mean 2 spin half particles, so you have doublets, and then you get 1 triplet and one singlet. Okay, grouping them. And if you group like this, you again get two doublets. So I mean, this is not grouped. This is not what you call grouping, right? Grouping means getting something new when you group them. So similarly here also you can think of it like this. So 3 cross 2, uh, instead of getting two triplets, uh, grouping them should give something else. So that's why we get a quartet of spin 3 half, spin 3 by 2, and then a doublet. Does this make sense? I don't know if this is the right explanation, but I think this is what should be. But yeah, I can look into it more. I'm also not very sure. So I don't know why my speaker is not working. Uh, hmm.
So can you hear me?
Yeah, now I can hear you. Can you, yeah, can you now talk?
Yes, just I thought that 4 plus 2 is required because we are trying to group half particles, half spin particles.
Mm-hmm.
So, but if we group them in triplet 3 plus 3, we won't get one of the possible spin values as half. That's why we need 4 plus 2. That's why we need to put it in a quadruple, I guess.
Uh, no, so I mean that is then why we get a when we group two spin half particles, why we get a triplet and a singlet. Here we don't get a spin half doublet, right? So that is not true. So what you are saying, you're saying because we are grouping three spin half particles, we need to get a spin half particles after grouping. That's what you are saying, right?
Yes, sir.
No, but that is not. That is not true. You can get anything. So, for example, here when you group together two spin half particles, you get one spin half and one spin zero particle. Sorry, one with spin one and one with spin zero. So a triplet and a singlet. So that is not true. But I think there must be something else to it. But naively, I think because we already have you know uh, we already have here triplet grouping together, we should get something more. Okay, we should not get the same thing again, because in here in this case, because we have a doublet and we have a singlet and then we are grouping, so in this case it is fine, we have only one option, just two. But since here we have two options, either 3 3 or either 4 2, so nature may prefer this one. Okay, but yeah, this is also allowed, this is also allowed, this is also there. uh, but what we have seen experimentally, that this thing is observed in the nature. So this 4 plus 2 plus 2 structure. So that's what we Uh, so when you form this spin half baryon octet, you have three spin half particles, right? I mean, for the quarks, you have three quarks, U, D, and S, right? And you get a baryon octet from them. So, yeah, I think this is the case. Now, okay, so this is how you combine two spin half particles, or combine representations of groups. So spin two SU2, sorry. So SU2, combining two SU2 groups will give you this uh, kind of algebra. Okay. Now let's go to SU3. Okay. So again, SU3 will be just the special unitary group of 3 cross 3 matrices, and so again it will have some generators, it will have their bases and all. But so why we needed SU3? Why we are not satisfied with the isospin group? I mean SU2 of isospin group. Why was it not enough? Because uh, people saw that there were some particles, for example, this sigma plus minus, or so these are uh, very stable, because they were created via strong interaction, but they were decaying via weak decays. Okay, so something was off about them, and people thought there must be another quantum number associated with them, which they called this strangeness. So strangeness uh, is another quantum number that was introduced, and so you have isospin group SU2, and then you have to account for this strangeness also. So that's why that's why we needed SU3. Okay, which will account for this strangeness quantum number also. And this SU3 group, this SU3 group together all the neutron, proton, sigmas, lambda, and then cascade into a octet. Okay, so like we had like I said, the SU2 of isospin group together neutron and proton. Similarly, SU3 of isospin and strangeness group together these many particles, these many baryons. Okay, and that's how we get these baryon octet. So here the neutron proton lies there, sigma 0, lambda is also here, sigma plus, and then cascade minus, cascade 0, right? This is the iso spin axis I3, and this is the strangeness. This we call baryon octet. Okay, so baryon spin half baryon octet, this is called. And then we have something called spin 3 by 2 baryon decouplate. Which is inverted pyramid. So here we have deltas, and then you have sigma, then you have cascade, and then here something interesting happened. So people predicted this particle called omega, and then later it was discovered. So this was the power of this group theory introducing into the particle physics. So group theory comes because of these symmetries, and just because of these symmetries, and just to have consistency, you see that we discover a new particle theoretically, and then it is observed in experiments. So it seems like nature also prefer having symmetry everywhere. So it was a triumph of you can say theoretical particle physics at that time. So these things were discussed in the lecture, so I am not going into the detail. But I just wanted to make some pictures clear. I don't know if I have made it clearer or I confused you. But yeah. So do you have any question?
No, sir.
Yeah, you should go and read some books that will make these things more clear. So you can read Griffiths. So first you should read Griffiths' Quantum Mechanics, the spin half algebra basically, and then Griffith has also elementary particle physics book. Where these things are discussed in detail. Or you can read Haljan and Martin's Quarks and Leptons book. Okay, so these things you can read, and you can get some more insights. Okay, so yeah, now let's go over some basic problems. So the first problem we have is this. So we have these delta hadrons. So this belong to, I just showed you a spin isospin 3 half group, and the quark content is of delta plus plus is UDD. UUD, 2 up quarks, 1 down quarks. Okay, and So its state, let's consider its state vector as, I think it is mistyped. It should be UUD, right? Yeah, like this. And then what we have to do is we have to use the isospin lowering operator to get the state vector of delta 0. Okay, so that means you have to apply this isospin lowering operator 2 times, right? So I minus on delta plus plus should give you some constant and then delta 0, right?
Sir, for delta plus plus shouldn't be UUU, the quad content.
Is it UU or is it UDD? Wait. UUU. Its charge is +2, right?
Yes, sir.
Yeah. It should be U. Yeah, then here is the misprint. Yeah, you are right. So, okay, yeah. So this we need to do. So in the lectures, this lowering operator is mentioned. I mean, it is discussed. So generally, what happens is if you apply a lowering operator on a state with isospin I and third component of isospin I3, you get this is the coefficient, this is the constant I plus I3 and I minus I3 plus 1. Okay, and here you have I, and this third component of isospin is getting reduced by 1. So this is what lowering means. So you are going from one state of the quartet to the another, applying this lowering operator. So these operators are there for are there in for each group. So in SU3, SU2, everywhere you have lowering or creation operator. These are called ladder operators. So this comes with the algebra of generators. Okay, now so yeah, this is our general expression. Now we want to apply it on the delta plus plus. Okay, so so yeah, first let's apply it on delta plus plus with UUU. Okay, so no, first let's apply on the baryon and then we will apply it on the quark separately. Okay, so I minus on delta plus plus. So delta plus plus has I equal to 3/2 and I third component of isospin is also 3/2, right? And this will give you in the coefficient. So 3/2 is just 3, and then 3/2 minus 3/2 is 0 and then 1, and you will get I equal to 3/2 and I3 equal to half, right? Then again, if we apply I minus on this, So that is applying I minus on this thing, right? So we have under root 3 I equal to 3 by 2, I3 equal to half. Okay, so let's take the constant root 3 outside and applying I minus on this state. So again, so you have I plus I3, so 3 by 2 plus half will be 4, 3 by 2 minus half, so will be 1, plus 1 it will be 2, so under root of this, and here you will have I equal to 3 by 2 and I3 equal to minus half, right? So finally what you get is, then you apply 2 times the lowering operator on delta plus plus, you will get, so under root 3 into under root 8.
Sir, under root 4, sir.
Where? Here?
Yes, sir. That 3 by 2 plus 1 by 2 will give you 2.
Wait. So what you are saying? 3 by 2 minus half give you 1, right? Here?
Yes, sir. Over there you'll get 2, and then for the I plus I3, that 3 by 2 plus 1 by 2 will give you 2.
Oh, sorry. Yeah. Sorry. Yeah. I forgot to divide by 2. Yeah, okay. Then you have just 2 root 3 and 2 root 3 I equal to 3 by 2, I3 equal to minus half, and which is, so this is the delta 0 state, right? So we wanted to just get this coefficient, so this is the delta 0. Okay, so this is this we have. Now let's apply the lowering operator on the quarks. Okay, so delta plus plus has this quark state. Now applying the lowering operator on u means applying the lowering operator on, so all of them, so you know quarks, in the so here should we consider the isospin of up quarks as should we consider them as triplet, or should we consider them as doublet of U and D? What do you think? It should be doublets, right?
Sir, why doublet?
Because in the problem it is not mentioned, but I'm guessing that by looking at the options that we are just taking 3 isospin half particles to basically but if we apply 2 times the lowering operator on u, what will happen? If we are considering spin half doublet, we cannot do that, right? This is little strange. Wait, something is missing. Strong isospin 3 half group. Hadrons. So, yeah, I mean, okay. So here the problem says hadrons delta plus plus delta plus delta 0 delta minus belong to the strong isospin 3/2 group. So it clearly says that the isospin 3 half group only group together these 4 hadrons together. Okay, it's not talking about the decouplet. It's just talking about the the quartet of these hadrons, and so it is just the uh, here the strangeness should not be present, because then you will go to the sigma and cascade. I mean, you will get the decouplet if you consider the strangeness also. So I think that is the clue. But then I'm thinking what will happen if you apply the lowering operator 2 times on a u state. So if you apply on half I3 equal to half, what will happen? Do you have an idea?
So not exactly. You'll get the constant as 1.
Yeah, constant will be 1. No, but I mean, applying 1 time is fine, because this will go to minus half. But I'm thinking what will happen if you again apply I minus on this? It should give 0, right? But 0, I mean,
0. So I will be 1/2 and I3 will be 0.
yeah, but 0 is not there, right? It is just the it's just the doublet. 0 state, I3 0 does not exist. So you cannot, I mean, this operation is not allowed basically in this case. Right. Okay. Uh, No, wait. maybe I am thinking it in a wrong way.
We have to apply the reducing operator to all three U's, right?
Yeah. I mean, one by one. Mm, yeah. Okay, maybe can we write it? I mean, so applying the lowering operator on this does nothing, right? Maybe it spit out the same thing. I forgot what happens. Because there are no states below this, so it should not affect it, kind of. If we assume this and then we calculate, let's see what happens. Right? Yeah, let's see what happens. If we get any option, then our assumption might be true. So, okay. So first application of the lowering operator. Okay. So these three all have I equal to half and I3 equal to half. This is for u bar. I mean, this is the first u, this is for the second u. So I am gonna write just 3 times. Hello. Oops. Hi Devi, can you unmute yourself?
Please.
Thank you. And then yeah. So this is what we have. Okay. Okay. Now what you will get. So first we apply the lowering operator on this one, keeping these two unaffected, and we will get 3 terms. Okay. So let's see how we do this. So in the coefficient it will be just root 1 under root 1. Yeah, you can check. And then here you will get half I3 minus half. These two will be unaffected for now, so these are same as above, plus again same thing. So the first will be unaffected, then second will be I equal to half, I3 equal to minus half, third will be unaffected, plus these two will be unaffected, and 3 equal to answer. Okay, so this is how you do this calculation. and so let's write what we get at the end. So this is the d, so duu plus udu plus sorry plus uud. So first application of lowering operator give you this. Okay, now let's apply again the lowering operator on this. Okay, so now this will be a very long expression, so let me just let me try to write it. Okay, so I minus on first this state, so if we assume that I minus on d do nothing, so it will basically it gives you the same. If you assume this, then let's see what happens. I think that should be the, yeah, I think that assumption should work. Okay, so then if you apply here, what will happen is, so again in the coefficient you will always get under root 1, right? And I'm not going to write in detail. So we know that one lowering operator takes u to d, so here you will get first d du plus dud, right? From here, is it right? The
You
first
should also put DDU, right? Sorry, DUU, right?
duu.
Yes, sir, because first you do it on the first part, but it doesn't change it, so it will
Okay.
just say
Yeah, that is also, I mean, that should be there. So then maybe we should, yeah, but I'm just looking at the options here, and none of the option has 2u quarks. So maybe then this thing reduces it to 0, not the 0 state. This thing just gives 0, I think. Lowering further gives you 0. I think this is right. Do you remember this? If you have Griffith's quantum mechanics lying around, can you check what happens to this? This also becomes 0, right? When you consider the lowering and raising operator for the harmonic oscillator states, this is what happens, right? I guess.
I'm not sure. I have a PDF of the book though.
Yeah, this is what happens. I remember it. Yeah, and it has some expense. So I think this is also true here. So lowering operator on D should give you just 0. So that's why the duu will not be there. Okay, and similarly you will have from here you will have ddu plus udd, and from the third one you will have dud plus sorry plus u dd. Okay, and you can see that there are two terms of each type. So 2 into ddu plus dud plus udd. Okay, so this is what happens when we apply 2 times the lowering operator on the UUU state. Okay, so from this expression you had, so let's combine these two expressions. So and you have 2√3, right? It was, yeah. So from these two expressions, what you get is delta 0 should be 1/3 of ddu right. I think which is the expression this.
Also, yes, sir.
Okay, so yeah, I don't know if it is how you do it, but I think it looks correct. But yeah, once check the calculation. Do you get some factors of coefficient in these? I don't know. You should not get, right?
No, I didn't get, sir. Even I was calculating alongside with you. I didn't get.
Okay, then it's fine. Okay, then yeah, this is the correct option for us. Why I think that okay, yeah, I think, yeah, then this should be the correct answer. Okay, but yeah, just check if this is true for the lowering operator in case of this harmonic oscillator thing. I mean, the algebra should be same, so if this is true, then this should also be true. But yeah, I remember this something like this, but yeah. Okay, then let's go to next problem. This is a simple problem based on the this Gell-Mann-Okubo mass relation. So I think sir has done this in the lectures. So this this mass relation is just relating the mass of neutron with mass of cascade with mass of lambda and mass of sigma 4, right? Just you can put everything and you can find the mass of sigma. So I'm not going to do this. It's simple, right? So yeah, this formula is not uh, not the original Gelman-Okubo mass relation. It is derived from this mass relation. This relation has some constants, and then you can derive it. I mean, this is done in the lectures. You can go through it if you have not. Uh, so yeah, this is easy one. Simple calculation. Okay. Then yeah, there is one problem on Rutherford scattering. So also I think in the lectures there is a discussion on the corrected differential cross section of Rutherford scattering. So in this expression, so this is the total corrected expression. Let me write it once, because this is very important, and so I mean, just to remind you what all these terms means. And 1 minus q square so first, I mean, this is the corrected expression for Rutherford scattering cross section. So why this modification? I mean, this term from which is called d sigma d omega by of mod. I mean mod. So mod scattering cross section. Why this comes? Do you remember?
So accounting for relativistic effects.
Yeah. So yeah, if the velocity of, I mean, so if the beta factor reaches around 1, so then you have to consider this mod modified cross section. Okay. And then why this one?
So I think, if I'm not wrong, I think it's for accounting for the recoil.
Recoil of what?
The recoil of the target particle and the beam.
Yeah, I mean, basically the recoil of the nucleus, right? So, but the energy here, this energy is energy of what? Do you do you know?
So that's the energy for the electron beam.
Yeah. Yeah. So I mean, if this electron, if this E is very less, then this whole terms become just 1, right? So if the energy of the beam is significant, then this factor comes into play, and it also depends on the theta. So this theta is what? This is the scattering angle basically, right? So for example, here you have the sine to the power 4 theta by 2. The scattering angle, you have the target and then some solid angle, and this is your theta, right? So this is the theta. Here the incoming beam. So yeah, this is due to the recoil of the nucleus. And then why this?
The spin, sir,
The spin of what?
the nucleus, I guess, the target.
By the way, wait. You said the d sigma d omega is just due to the relativistic effects?
Yes, sir. Only the relativistic effects, right?
What about the spin of electron? Where does that get accounted for?
So the spin of the electron is not that relevant, right?
Are you sure? because the d sigma d due to mod um, it has, I don't know, I think I remember that this also accounts for the spin of the electron, but I'm not sure. Okay. Okay, so this you are saying the spin of the nucleus, right?
Yes, sir.
So spin of nucleus or the spin? So why the option says spin of proton?
Sir, maybe here they're taking only the hydrogen atom as the target.
Uh, Not really. So when we were studying the cell model, you saw that the overall spin of the nucleus is governed by the spin of unpaired proton or neutron. I think that is what comes into play here also. Because otherwise, all the protons and neutrons will be paired, right? I mean, so it should be the spin of nucleon, unpaired nucleon, maybe. But I think this option is a little bit confusing to me also. I mean, it is my guess that the unpaired proton or neutron should affect the overall spin of the nucleus, right? From the cell model, that's what we got. But anyway, I mean, this is the correct option here. But just to think about it, uh, I'm also not sure. But it doesn't make sense to say only the spin of proton, unless we are considering only the hydrogen atom. Okay. So yeah. This is also discussed in the lectures, but not in much detail. I think it is not derived because I think deriving it will require a very long procedure. So you can take a look in some books. I think there this explanation should also be there. So one should look for that. Okay. And okay, one last problem for today. So the question is, when electron scatters on proton in the Rosenblatt formula for scattering cross section. So this is also discussed in the lectures, the Rosenblatt formula for scattering cross section. So the Rosenblatt formula takes into this Rutherford scattering formula assumes the nucleus to be a point-like object, and the Rosenblatt formula consider nucleus as a extended object having a charge distribution, and then when you have extended charge sphere, it might because it is charged and the charges are moving around, so there might be some magnetic moment also associated. So this accounts for those effects, right? And in the formula there are two basically notations, G and GM. and they are related to one G is related to the electromagnetic effects coming from the charge distribution, and GM is related to the magnetic effects. I mean, basically coming from the magnetic moments distribution of the proton, right? So yeah, I mean, these are just to remind you.
So then option 2 should also be correct.
Option 2, G and GM being non-zero indicate the deviation of proton from point particle. No, this is not for proton, right? This is this is for nucleus, right? Oh,
Yes,
okay,
sir.
okay, okay. When electron scatters on proton, yeah, yeah, yeah. Then this is also this should also the second option should also be true. But third option, what does it say? GM being non-zero indicate point like no, no, no. This is wrong. Yeah, yeah, this is true. No. Yeah, these two options should be true. Right.
So
Okay.
fourth one is irrelevant of
Yeah,
G and GM, right? Like relativistic effects do not affect G and GM, right?
yeah, it should not. Okay. So yeah, that this is the last problem that I have. So do you have anything to ask so far? Today I didn't keep many problems. Uh, yeah, I mean these lectures are not very detailed. I mean that's what I got the expression, but it introduces you some of the basic things, and later you can again go and read about it in details. For example, basically it motivates you to further read these things. Obviously everything cannot be I mean captured in these lectures, 3 hours per week. But yeah, it's a nice introduction, but yeah, I mean, if you go through the lectures, then you should be able to understand, and I mean, it will be good to discuss uh, here in the live session the concepts that are there in the lectures. Otherwise, I mean, I cannot go. I mean, I cannot teach all the lectures here in 1 hour. So I assume that you all have gone through it, and then I will just, discuss something that I thought is not very clear, because I myself go through them and try to get an idea of what should I mean what is missing from the lectures, and I try to do that here. So I don't know if you like it or not, or do you want me to change my style of doing what I do here? So please let me know also that. Is it fine what I discuss, or should I do more problems and less of the concept or discussion? What do you like?
So along with the description, like more problems, like not
Okay.
not saying ki no
Mm-hmm.
description, but like few
Yeah,
more
yeah,
problems.
yeah. Okay, okay. Yeah, yeah, I'll try that from next week. I also thought that, yeah, the problems are less. But the thing is, I mean, uh, yeah, in this, in last, from last 2 weeks, I cannot see which kind of problem I can give. Like, for example, so here you have these big formulas, and but these are not, derived, or anything detailed has been told in the lecture. So I cannot, like, put some problem together uh, which will explore these problems. So, for example, one can, one can give some problem where you have to calculate the differential cross section, maybe for a real scattering problem of electron and proton. That can be done with this formula, but then again, to do that problem, you have to little bit go into the derivation of this thing, because you have to understand how these things came about, right? So that's why I could not keep more problems, I mean more detailed problems on these concepts. But yeah, I'll try that from the next week. Maybe I'll discuss something, and then I'll do some more problems. It will be a complementary to the lectures, basically. Okay, so yeah, thanks for the feedback. Uh, so yeah, let's. If you don't have anything else to discuss, then let's end this session today here, and meet again next Saturday. Okay. So yeah, bye everyone. Thank you for joining.
Thank you, sir. Bye, sir.
Bye.